In one of the previous modules, we were able to make a not so subtle connection between the electric field and the forces we were used to dealing with in classical mechanics. In this module, we're going to do something different. We're going to try to make a connection between electricity and energy, including the conservation of energy. A discussion of energy usually starts with a discussion of work. So how do we define work again? Imagine you have some particle. We're not even talking about electricity right now. This could just be any particle. Now suppose for a second that the particle here feels some constant force, which acts over some linear distance like this. Well, the distance the particle travels here is better represented by a displacement vector. Let's call this vector s. The work done by this force over this displacement is given by F dot s, where F is the force vector. Remember that work is a scalar, just like the dot product. So if we imagine the angle between the force and the displacement as theta, then we can also write the work done here as F times s times the cosine of theta, where we only have to deal with the relevant magnitudes. For the calculus nerds, the work done due to a changing force, a force that's not constant, over some path like this, is given by the integral of F dotted with an infinitesimal displacement ds over the entire path. You just integrate or add up all these little f dot ds's and you end up with the work done. This is what's called a path integral or a curve integral, since it involves integration over a specific path. Now that we've reviewed how work is related to force, how do we think about this in the context of electricity? Let's consider the calculus-based and non-calculus-based versions separately, but still the same equations we were just talking about. Well, we were just talking about how forces were related to work, so what happens when we just plug in the electric force in place of the general force we have here? This is now the work done by the electric field on a charged particle with charge q, in moving it through some displacement s. At the top, we have a non-constant electric field, and below we have a constant electric field. Now we can go even further with this. We know from classical mechanics that if we're dealing with some gravitational force mg, where g points in the downward direction, the work done by the gravitational force might look something like this. It's mg, but then dotted with the displacement this particle went through. Right? That's just the work done by the constant gravitational force through this displacement. It's just F dot s, or mg dotted with the displacement. Since g and the displacement act in the same direction here, g dot s is just the magnitude of g times the magnitude of s. The angle between them is 0 and the cosine of 0 is 1. The magnitude of s here is just the initial y value minus the final y value. Since the particle is going down, this would give you a positive value for the magnitude of s. Now this expression kind of looks familiar, I hope. What we found here is the work done by gravity on the particle as it moves downwards in a uniform gravitational field g. We recall that in a uniform gravitational field near the surface of the Earth, the gravitational potential energy of the particle is mgy. So here we have the work done by gravity on the particle is the initial gravitational potential energy minus the final gravitational potential energy. Rearranging a little, we see that the work done by gravity is equal to the negative of delta U, or the negative of the change in gravitational potential energy. Now, sidestepping this for a second, let's take a look at two expressions we're familiar with. One of them is for the gravitational force between two masses, and the other is for the electric force between two charged particles. They're nearly identical up to a constant. It's just that one of them is dealing with masses, and the other one is dealing with charges. As a result, all of the gravity dynamics we dealt with in classical mechanics can easily translate right over to electricity. We saw how the forces were related in this way too. mg was related to qe, in that g is the gravitational field and E is the electric field. Now we're about to apply the same connection to work and energy. The work done by gravity is equal to the negative change in gravitational potential energy, like we saw earlier. Our connection here then is the work done by the electric field is equal to the negative change in electric potential energy. We already talked about an expression for the work done by a varying electric field on the left and a constant electric field on the right. So just appending a negative sign to the front of each will give us the change in electric potential energy. Right now, we're sort of just adding little snippets to our toolbox, but we'll go over much more of the intuition behind these definitions in a few lessons. There's one more thing we can do now, and this time it's probably something you didn't see at all when you were working with gravity in classical mechanics. This expression we have here, whether you're looking at the calculus or non-calculus based one, is dependent on a charge in front. So we can write this as per unit charge, and we end up with a new expression. The change in electric potential energy per unit charge is equal to the negative of the electric field dotted with the displacement, or integrated in calculus. And now this is what we call the change in electric potential, V, or the potential difference, delta V. Okay, kinda odd. A natural question here is why even define something like this? We never defined the equivalent version in classical mechanics. Whenever you dealt with classical mechanics, you probably never saw a definition for gravitational potential. We know the work done by the gravitational force is equal to the change in gravitational potential energy. This leads us down the same chaotic rabbit hole we kind of saw before. And now defining the gravitational potential as the gravitational potential energy per unit mass, we end up with the following. The gravitational potential difference between 2 points in space is the gravitational field multiplied by or integrated with the displacement. What a weird looking concept. So what gives? Why didn't we stress gravitational potential way back then? And why are we stressing electric potential now? Before, when we were dealing with problems involving gravity, we usually weren't dealing with wildly varying gravitational fields. We have the uniform gravitational field near the surface of the Earth, so that took us through all the problems we wanted to solve near ground level. But for interplanetary style problems, where we have to deal with orbits and things like that, defining a sense of gravitational potential just never really would have helped us in any way to solve basic problems. You could do it, but why? On the other hand, when we're dealing with electricity, we've decided to define this idea of electric potential because we can frequently run into situations where the electric potential is constant along some useful region. We don't know that yet, we're still discovering all this, but that should at least whet your appetite for now. We've made a lot of headway, but we still have a lot of questions left to answer too. For one, the title of this video is What is Electric Potential? But I still haven't even answered that. I've only given you an idea for what electric potential difference is, or what delta V is. The individual potential V itself, we don't really know what it is or what it means just yet. Until next time.